Okay, hey folks, continuing along. So this will be a short video introducing this concept of the Clausius inequality, which manifested from the Carnot cycle, but it's also another way to prove the second law of thermodynamics. So this is more of a thought experiment, but a really useful thing. So recall, more work is done when a change is reversible than irreversible. So we proved this when we talked about the reversible isothermal expansion of an ideal gas, if you recall. So using absolute value signs to not conflate like the exothermic, endothermic, negative, positive deal, we'll say dW reversible, absolute value, is greater than or equal to, we'll include that as well, than dW. So we'll say dW corresponds to irreversible. And I'm not putting that there just for convention. So that's typical in thermodynamics. So, and then of course, if we were talking about expansion, we could get rid of those absolute value signs, right? And we could say negative dW reversible still has to be greater than or equal to negative dW. We could say the same thing about their positive quantities. And then rearranging this algebraically, we can say dW minus dW reversible must be greater than or equal to 0. So this is the same thing that we just said. More work is done when the change is reversible than when it is irreversible. And in this case of expansion, if we take dW irreversible minus dW reversible, that has to be a positive quantity. So we rely on internal energy now to continue this discussion, which recalls a state function. So it does not matter if the change was given reversibly or irreversibly, the result will be the same. So we can say dQ, which is irreversible, plus dW, also irreversible, must equal dQ reversible plus dW reversible. So again, for du, it doesn't matter if the change was reversible or irreversible. It is one and the same. And so now rearranging this expression to get like terms with like terms, we have dW minus dW reversible. And that equals, and so again, just following this algebra, dQ reversible minus dQ. Okay. Well, we just said up here that dW minus dW reversible must be greater than or equal to 0. So we can say now dQ reversible minus dQ irreversible must also be greater than or equal to 0. And rearranging algebraically and dividing both sides by t, that allows us to say dQ reversible over t must be greater than or equal to dQ irreversible divided by t. And if we recall the thermodynamic definition of entropy, ds equals dQ reversible divided by temperature, we've now arrived at the Clausius inequality. So I can replace this with ds, which says ds must be greater than or equal to heat supplied irreversibly at some temperature. And so this is our Clausius inequality. And another way that we can think of this, recall another statement of the second law, is that entropy must increase for an isolated system in the due course of a spontaneous process. Well, in an isolated system, dQ equals 0, right? So in that case, the corollary of the Clausius inequality says ds must be greater than or equal to 0 in the due course of a spontaneous process that is isolated, and we can see that that's true. We've proven the second law. So a short little thing there. And then we can also use the same thing to recognize that simply when we have a hot object in contact with a cold object, the hot object will always deliver that heat spontaneously to a cold object. So for example, we can write the second law saying ds total equals ds system plus ds surroundings. And we recognize for a spontaneous process that must be greater than 0. Okay? So now noting here that the entropy, we're going to call the hot source my system, and of course everything around, including the cold sink, are the surroundings. Okay, so we can say the following. So we now can say here that ds, recognizing that it must be greater than or equal to, that it really, I should just say that it should be greater than the following. So let's see, that becomes, in this case, dqh over th, that's my system, plus dqc over tc, that's my surroundings, that's the letter C. However, remembering that dqh equals negative dqc, as we can see right here in this diagram, we can make the following substitutions. ds is greater than or equal to the following. dqh over th minus, let's see, what did I do? Sorry, I'm following along here. Let's see, actually, yes. So let's make that substitution. Apologies. So we'll note now that this was my system, right? This is my surroundings. We said dqh equals negative dqc, so let's make that substitution. So negative dqc over th plus, and now that will be positive dqc over tc, so I've just brought those things down. And if we arrange these things algebraically, we end up with the following: 1 over tc minus 1 over th times the quantity dqc. So now if we think about this, because we're specifically saying tc is cold, th is hot, it follows that tc is always less than th. And what that means now, 1 over tc minus 1 over th is always going to be greater than 0. Thus, we've proven ds is greater than 0. So anytime we have a hot object in contact with a cold object, it delivers heat spontaneously. We knew that from our common everyday experience, but we've got to use all of this math to prove that that must be true. Okay, so that's all that I wanted to do in this video. I'll see you later.